Second speaker today is Vaibhav Agrawal, again from ARM, based in Austin. He's a principal engineer at ARM, and he's going to talk about two case studies in formal deployment on ARM CPUs, instruction fetch and floating point data path. Vaibhav is a verification engineer at ARM in Austin. Prior to joining ARM, he was a design automation engineer at Intel and has a master's in EE from the UT, University of Technology, I guess, Austin, and a BTech in EE from the Indian Institute of Technology in Delhi. So we're going to hand over now to Vaibhav.
Thank you, Mike. Thank you, Sarah. Hello, everybody. So, we're going to talk about a couple of case studies. So one is for instruction fetch unit and one is for floating point, how formal was used differently for both of these scenarios. So starting with instruction fetch unit. So let's take a look at what is the instruction fetch unit at a high level. So it contains your instruction cache with your tag and data rams, which interface with your decode unit and your L2 unit for requests and responses for misses. You have your branch resolution unit, which will resolve branches coming from issue queues. You have your predictors and next fetch address generation logic. You have your return stack, which processes the return branches. You have your instruction TLB, which will interface with the MMU. Your Snoop logic, processing your cache maintenance operations, TLB maintenance operations, and only debug array reads. You have your commit unit interface, which is basically your reorder buffer, sending in flushes, commit flushes, that is. Architectural registers, of course. And then you partition this logic into three pieces. One is your next fetch address generation logic to the left side, branch resolution, and your fetch pipe. And then you have your fetch queue, which is receiving the next fetch addresses from branch predictors, storing them and passing them on downstream for cache access. So all of this is your traditional instruction fetch. And then what we did in this project that I'm talking about is we added a mop cache or a trace cache. And this essentially contains decoded instructions as they are coming from the instruction decode unit to the right, which is the gray box. So it's filled with decoded micro-ops. And this was a new critical piece of functionality added primarily for performance. And this was quite a disruptive change to the design. Now, the reason I'm telling you all of this is to get the point across that this is a pretty control-heavy design in the instruction fetch unit. And it has many finite state machines interacting with each other, and mop cache was a new feature which was added. And the project timeline was pretty aggressive. This was a performance-intensive change, which was supposed to be taken out pretty soon. And while simulation remained the primary workhorse, it still remains the primary workhorse in terms of finding bugs. The point is there are no dearth of bugs in this particular design. As Vikram mentioned earlier, the memory subsystem and fetch typically have a lot of bugs that formal can contribute towards. Now, so what we decided to build a formal test bench around this hierarchy encapsulated by the red rectangle. And the green check marks denote some interfaces on which we had some checking. So we were checking the instruction delivery from the instruction cache, mop delivery from the mop cache, and then also the instruction decode unit, which is the gray box to the right, has to decide whether to send mops or instructions forward to the rest of the pipeline, the CPU pipeline. So it has to order instructions against the mops coming from the mop cache, and that itself requires, that's a pretty control-intensive logic, and it was quite buggy to begin with. So that green check mark to the top is essentially checking the switching between your instruction cache and mop cache in the decode unit. So we had checkers around that too. In terms of stimuli, that is what kind of stimuli we enabled in the test bench. So if you will focus on these red circles or ovals as they appear, so we modeled the commit flushes coming from the reorder buffer, the next fetch addresses coming from your predictors, then your branch flushes coming from the branch resolution unit, your mock cache fills as coming from the decode unit, that is the decoded micro-ops, as they are filled into the mock cache. Whenever you have an instruction miss, then you send out an L2 request for a cache line, and the response, that interface was modeled. Your snoops were modeled, and then of course the stalls from the decode unit for both instruction cache and mock cache were modeled, and your TLB misses, the request and response were also modeled. So all of this was modeled in the test bench for formal. And again, the primary target for verification here was the disruption caused by introduction of this mock cache or the trace cache and how it affects the overall functionality. Now, why formal? As I explained, there was no dearth of bugs. So any bug that was found by formal in this parallel verification effort with simulation would mean there is that much less work to be done by simulation, because the timelines are pretty aggressive. So that's essentially your shift left. This is the buzzword these days in the industry. So, you basically earlier time to market. Now, one of the problems with formal is, as Vikram was explaining earlier, you have to manage complexity of your test bench, and you have to, as much as possible, make the test bench more efficient. And one definition of efficiency for formal can be to improve the reachability of state space, both in terms of time and sequential depth. So what that means is you want to get to your state space using your formal test bench as soon as possible and in as little cycles as possible. So towards that, we made several attempts in the test bench. Key capabilities were added to the test bench to reduce complexity. For example, we reduced the sizes of all the tables or hashes in the design. This includes your caches and ITLB, your TLBs. The actual mop line, the mop in the mop cache, the size of that was reduced because formal did not need to process the entire mop. Various structures in the design were actually preloaded. I'm using the term preloading, which is a simulation term, but for formal terminology, it's actually initial value abstractions or reset abstractions. And then we reduced the actual virtual address and physical address space that was exercised with formal. Formal did not need to see the entire VA and PS space. And the actual data space was also reduced, and data for instruction fetch is actually mops and instructions. So not all mops and instructions were enabled. Formal did not need that to find control-intensive bugs in the pipelines. Here is a sample checker that we developed. So essentially, many ordering checkers were developed for this particular test bench. I'm going to go over this one checker, which was checking for ordering for mops as delivered from the mop cache. So imagine you have two tracked virtual addresses, and a tracked virtual address is essentially constant. It remains constant within a trace, but formal allows it to vary across traces. So it's a pseudo constant. Think of putting a $stable constraint on your signals there. Now you add a constraint on these two virtual addresses that they're always in program order. That means that your tracked virtual address 1 is always followed by tracked virtual address 2. What that means is if your VA1 is a taken branch, then VA2 must be a target. Another constraint is added where you marry specific mops or micro-ops to these tracked virtual addresses. So at VA1, you must always have mop1, and at VA2, you must always have mop2 in the mop cache. So essentially, a marriage has happened here between the addresses and the mops for these two tracked addresses. And for every other address in the mop cache, you fill it with or preload it with a third mop, which is same across all the remaining addresses. And then this constraint is added for both your preloading or reset abstractions and also for your mop cache fills as coming from the decode unit. Then your checker simply becomes that whenever you see the first colored mop being delivered to instruction decode, then that must be followed by your second colored mop. So this becomes a powerful end-to-end check, an ordering checker. And then we had, as I said, we had several of these ordering checkers, and to manage conflicting constraints across these ordering checkers, we used oracles, which are again pseudo constants, which can be used to manage these conflicting constraints. So what this slide is talking about is so formal has a problem. You can say a problem. I mean, when you try to reproduce a particular trace with formal, there's no guarantee that it will end up generating that same trace. So if you are presenting a bug to a designer and the designer is not able to reproduce the same trace, then how will you verify that he has actually fixed that problem? So towards that, we developed a methodology where we were writing a directed assertion in some sense and providing that to the designer to achieve two things. One was to reduce the time it took the designer to actually generate the fail, even though the original time was, let's say, 4 hours or 5 hours. And the second goal was to make the failure more reproducible. And the way that was achieved was, if you see the highlighted section at the bottom, the directed stimulus sequence was captured from the original trace for key signals in the design, and that was added as in the precondition of the original assertion that failed. An interesting methodology here. All right, now in terms of the value added by formal on this particular design, so we had about 100 bugs that were found by formal here. Over a period of, I would say, maybe 8 to 9 months, 10 months maybe. And most of these were found either by end-to-end checkers, the ones that I described earlier, or by embedded assertions, which are white box assertions developed by designers. And about the remaining 20% were found by interface properties that Vikram described earlier. And in terms of functionality, about 35% were found in the mock cache, which is the section in yellow, and about 37 plus 19, that is the blue section. So roughly 56% were found in the instruction cache, and that's because the presence of mock cache has to be accounted for in the instruction cache logic. And so it's a huge change to the instruction cache logic itself. And then some remaining bugs in some miscellaneous areas were also found. So again, in terms of value added by formal, designers actually used formal for bring up. So for example, one of my designers was using formal until the mean time to failure in formal became more than 20 minutes. And then he said, now it's more productive for me to use the simulation environment because he can get failures faster. So formal was helpful for him, for example, so every time he would develop a new feature, he would use the formal test bench to clean up his design for about 2 to 3 days until the mean time to failure was about 20 minutes. And then the verification team worked closely with the design team in some scenarios where it's not the designer himself, but the verification guy is running formal on a particular feature and trying to clean that up before the feature is handed over to simulation for more bug hunting. And then, of course, formal found some corner case bugs. In this case, we had about 5 to 7 corner case bugs out of the 100 that we found using formal, which would have been difficult to find using the constrained random unit simulation test bench. So the question is, so essentially the learning from this slide is that formal can complement simulation. It doesn't need to be one versus the other. Now the question, you might think, could simulation have found all these bugs? Maybe, but it would have been harder. And I mean, as people look at this data of 5 to 7 bugs or the 100 bugs, some people might react and say, well, that's great. You know, formal finds 100 bugs. That's amazing. What else can you do? I mean, how can I use formal better? Or some people might react in the exactly opposite way and might say, 5 to 7 bugs, really? That's all you could do with all this effort? And you're asking me to invest in formal just because of that? I mean, 2 different reactions, right? So for people who are skeptical still in terms of can formal add value, and they're wondering, well, I have a limited amount of resources. Should I invest in simulation or formal? That question is above my pay grade. I was just hired to do formal, so I did formal. But I mean, to throw some perspective on this, I mean, the simulation does hit a diminishing, the law of diminishing returns. I mean, you cannot just keep on adding resources on simulation and expect to get more and more value. It's good to add a complementary capability here, and really think about it. How much is those 5 formal only bugs worth? In our case, every one of those bugs could have been a cat A errata after we had passed on the RTL to our customers. And then how much is the shift left worth, early time to market. And like everything else, as Vikram was mentioning, the entire timeline that he showed, it is an investment and it takes time to bear fruit. So, I mean, some patience is required here and perseverance is required here. And it requires cooperation from both designers and the simulation-based test bench folks, because they are going to be the ones who are going to be debugging your bad assertions that they enable in simulations or traces that are not really genuine fails. So, I mean, some cooperation and commitment from them is definitely required here. And it requires commitment from management, which we had in Austin. We have in ARM. In general, ARM supports formal. And of course, finally, and I mean, needless to say, it requires a huge commitment on part of the formal verification engineer, because it's ultimately for the formal team to prove their worth. Switching gears to floating point. Just a bit of an introduction here. In 1995, we had this Intel Pentium bug, which cost about $500 million to Intel. And think about that. What will be a cost of a floating bug today to Intel or ARM? In fact, I mean, the understanding today is in the industry is that a floating point bug is unacceptable. There are high expectations of accuracy from floating point. There is little tolerance for a bug in that area. And if you think about it, if you want to exhaustively verify all of your input stimuli possible for even a half precision operations. Let's see, if you take a floating point add, which is half precision, 16 bits, even that to exhaustively simulate would require about 100 days of CPU time. That's a lot of cost in terms of machine time. And and then for single precision and double precision, you can forget about it. There is no way to exhaustively simulate those, right? So there is definitely a need for an exhaustive yet an efficient method for floating point data path verification. And these are operations like your floating point add, multiply, divide, square root, etc. So with that motivation, let's talk about sequential equivalence checking. So equivalence checking in general refers to verifying that your given implementation is equivalent to a golden reference model. And typically where it's used in the industry is for Boolean equivalence checking, which is for RTL to gate equivalence. Now, sequential equivalence checking is slightly different from Boolean equivalence checking, because in Boolean, you are able to map all your internal flip-flops or latches one-to-one. But in sequential equivalence checking, that requirement is not there. In fact, that is the power of the sequential equivalence checking. For example, if you look at the two designs on the left, the two flops, the corresponding flops between figures 1 and 2 are not equivalent. But if you were to do an end-to-end verification, then these two designs are equivalent. And you have to use a sequential equivalence checker tool to be able to prove that. All right, moving forward. So in our case, for floating point data path, we use two kinds of golden reference designs. One was an RTL from a design that was validated early on, like a previous design that has been in the market for a long time that we thought was golden enough tool. And then in another application, we took a C model from our performance model library that Vikram was talking about. And towards that, we use Mentor's SLEC tool. And the goal for our floating point verification using formal was twofold. One was to do just bug hunting, and to enable that, we developed some end-to-end test benches, no internal cut point mapping, and the design was treated as a black box, and it was very useful in shaking out bugs early on, most of the bugs. And then in some scenarios where the designer wanted it, we actually worked on to obtain a full proof. And for that, we actually need to do a detailed proof decomposition, because end-to-end strategy would not lead to convergence. And this was specifically true for your multipliers, your FMAs, divides, and square roots. So here is a sample of how a proof decomposition might look like. This is the case of floating point divide. So on your left, you have your C model. On your right, you have your RTL. And as any of you who would have worked with floating point might know, the divider is implemented in a way where you have to compute partial quotients and remainders for each iteration. And these are available both in your C model and your RTL. And to be able to do a full proof, you have to decompose your proof such that these intermediate quotients and remainders are actually proven, and there are cut points and map points on all of these. Just a high-level idea of how a proof decomposition might look like. Right, moving forward, we actually hired an industry expert in the area of theorem proving to do theorem proving based floating point data path verification, and this was quite different from the approach that I've talked about so far, where what he would do is he would stare at the RTL and understand the logic and develop a lower level C model based on the RTL. And then he would take the C model into the pour it into the theorem prover, and then mechanically prove that the algorithm for divide or multiply or FMA is actually correct. And then once he did that, he would then prove that the C model is actually equivalent to your RTL using a sequential equivalence checker. So a very different kind of an approach, but it's a much more scalable approach in terms of the design sizes and the complexity. Now, we did end up finding quite a few interesting bugs using this. Now, this doesn't look as rose. I mean, it's 100 in instruction fetch versus 11 in floating point. And so anybody who has floating point would know, deep corner case bugs are not as many, but each of these bugs were very meaty and would not have been caught by simulation. So while simulation still remains the primary bring-up vehicle for our design team, as Vikram was mentioning, formal is now an integral part of our overall verification methodology, though, in this area. In fact, here is an endorsement from a designer, and this is my last slide. So the designer mentioned that in addition to the elimination of floating point bugs, we are experiencing other benefits of our expanding set of formal tools. And the first bullet here is saying that it lets us design more boldly because he knows that formal will be able to verify it. The second bullet point says here that it frees up his time because formal can iterate over his design changes more quickly. So that's quite an interesting endorsement. That's all I had, folks. Thank you. I don't know if there's any questions.
Any questions, Augusto? Yeah, hi, Vaibhav. We have a question on 9.
Okay.
Were there any bugs missed by formal and caught by simulation for both the projects?
On floating point, I'd say no. On floating point, we actually put in one of the major goals of the formal and floating point was to be able to catch anything that was missed by simulation. So on that, I would say formal is the final net or the sign off. But on instruction fetch, the goal was not to find all bugs or to develop a proof, but the goal from the beginning was to augment simulation and to find any bugs that would be hard to find by simulation. Hopefully that answers the question.
Okay. There's another question on 9 from Ashish Dabari. How many full proofs, how many proofs in full were obtained on the IFU?
Sure. So as Vikram mentioned, so that statistic of 40 to 60% is generally true for all of our designs on which we do formal property verification. Now, I should say that the bulk of these assertions, so we had around 1,000 assertions overall that we were running formal on the IFU, and about half of those were designer written white box assertions. The other half was either interface properties or end-to-end checkers. And I would say bulk of the assertions that did get a full proof were actually designer assertions inside, and the interface properties and the end-to-end checkers would rarely get a full proof.
Okay, thank you. We do have one question from Bristol now. I'm going to hand over to Tariq.
Hi, Tarek Kurd from Huawei. How did you verify the floating point multiplier in Formal?
Right. So there are there are different approaches we can do. So it depends on the tool that you are using. So the Hector tool from Synopsys has a particular capability where you can actually map the design based on topology to a particular algorithm. And once you're able to do that, then it takes literally 5 minutes for their proof engines to verify that your actual multiplier array, the Wallace tree and the multiplier array, matches a particular type of algorithm. Let's say a radix 8, multiplier. But then that's a very tool-specific methodology. The general approach is to using a sequential equivalence checker is to break down your multiplier array into, so use some kind of an induction where you prove that you first take a 1-bit multiplier, then a 2-bit multiplier, then a 3-bit multiplier, and you use induction to prove that if your 1-bit multipliers are equivalent, then your 2 bits are equivalent. If your 2 are equivalent, then your 3s are equivalent. You take that approach to just prove your array. Once your arrays are proved equivalent, then you can black box the array and add a mapped point on the outputs of your black box, and then prove the rest of the the normalization and rounding logic separately in a final run. And the third approach which we used, which was developed by this theorem prover expert that we hired, he does everything in a very orthogonal way. He would basically take this, capture the design in a C model, port the C model into a theorem prover, and he would literally, like in high school geometry class and algebra class, as you would do a proof step by step using a paper and pencil proof for equations, he does exactly the same in the theorem prover. And then, and this is again something that he does. I cannot do that today. So, and then he's able to then prove that C model is equivalent to the RTL using a sequential equivalence checker. So 3 very different approaches.
Okay, good answer. Thank you. By the way, I can't remember doing that in high school, but we take your word for it. Just in case anyone is interested in Hector, and given that Synopsys are a sponsor, there were quite a few snug papers on proving multipliers in Hector from an Imagination speaker, I think, about 2 years ago. So there are snug papers on Hector and how to verify multipliers, but I think, as Vaibhav says, it's very tool specific. Okay, that brings us to the end of that talk. So we've got 2 more talks. So thank you to Vaibhav first. Thank you.